I have some slides I can go through on kind of object behaviors and ideas around that. And then, yeah, Vivian, you mentioned if there was time, then get some stuff that maybe.
Yeah, just very short, but no worries if we don't have time.
So
Okay, cool.
I don't have any slides, but I've been working on object behaviors a lot. So I have a lot of interesting observations. So
Okay, nice.
I don't know if I should interrupt and say, hey, I was thinking about this or that, or just let you go through it. But
yeah, no, I think interrupt as much as possible. And then I guess we can always, if
sometimes we do brainstorming.
it's
Yeah,
too
sometimes
slow.
it's like,
yeah,
it's brainstorming, and sometimes nobody want to get the material out. So anyway.
Right.
Anyway,
yeah,
it's
and
fresh
this,
in my mind.
yeah, so I guess this is just an attempt at kind of bringing together some different thoughts about graphs and sequences and how this relates to object behaviors. It's nothing really kind of new. It's more just trying to like kind of summarize a lot of the stuff we've discussed and kind of reframe it in a way that's hopefully useful. And in particular, kind of how are we going to actually represent behaviors in Monty or how they're represented in the brain. And part of this will kind of touch on kind of, yeah, maybe just like how far we can get with sequences and kind of how universal they might be. So I guess, yeah, after, for example, what you shared, Jeff, about how we can attend to changes, it feels like things like how we learn the object behaviors is a bit clear, but the sort of substrate that's actually representing object states is something we kind of still need to clarify. And in discussing this, I'm also going to kind of touch on how we represent kind of reference frames, morphology, the path integration space, whatever you want to call it, that we also have. So you have the series of states, the behavior, but at any given time, there's some kind of morphology that you are able to kind of predict what you're going to see if you move somewhere on the object. And so how that might kind of tie in with this as well. And yeah, as alluded to before, I guess it's just kind of a start of thinking about how kind of sequences might be useful for a lot of different parts of this.
Can you going to explain that?
Yeah, by double, triple roles, I just mean like lots of different things that they may be
you're going to walk through.
But
you're going to walk
yes,
through
definitely.
What you think about. Okay.
And then one other kind of related goal, I guess, is just there's lots of different interesting work out there on how you kind of represent structures. Everything from graph networks to hierarchical temporal memory for sequences and all these kinds of different things. And you don't need to have come across all these terms, whatever, but I just thought if these are things you've kind of come across, at least I found it kind of confusing, like how do these all relate to each other? And so I'm just trying to kind of maybe put a bit of structure to that. And in particular, kind of really look at the big ideas of kind of graphs and sequences, how these are kind of related to one another, and then how these relate to representing states and representing space. That was a kind of preamble. And yeah, hopefully I've not kind of assumed too much. That like part of the issue is like we've done kind of similar brainstorming sessions, many times over the years, and so I may assume, that you are fairly familiar with hierarchical temporal memory or some of these other things. So definitely stop me if I can clarify anything. So in terms of like how we might represent object behavior, I think one way you could frame it is this sort of graph view where we have a morphological model of an object, which is a series of nodes.
Are those nodes are locations and like
yeah, so those are our locations. Yeah.
Okay, because they're not like
features.
It's a continuous space, right? So it's not like there's 3 nodes or something. It's
yeah, although I mean we don't represent it in a totally continuous space, and we've also talked about how like as we get more hierarchy, we would expect this to be more sparse.
Maybe, but it's the space itself is continuous.
That it's embedded in isn't continuous.
Right, yes. There's a space in which we've located features at different locations in that space and other points in that space. We don't see anything.
Yeah.
Right. Yeah. Okay.
Yeah. And then if you wanted to encode behavior with a graph, you could lay down edges that connect nodes, not necessarily all the nodes. So that's just showing an example here where there's edges between these and edges between these. And then the behavior of the system could then kind of follow this, where the state of a given node, a given location, at a time point is going to depend on a series of things, which can be summarized as the state of the connected nodes based on incoming edges. So that's information from neighbors that's transformed by an edge affecting this node. Some like local actions. So this is kind of additional influence in the system. So for example, someone pushing, and then, and I should say for the edges, that includes like a self edge. And then it's not necessary, but it's potential that you could have some global state, like maybe some pooled state that's describing the object. You know, maybe it's hot, maybe it's cold, whatever. And that kind of influences at a more kind of global level all of the nodes. I'm not claiming that this is the way we should do it. I'm just trying to kind of describe like how, like one way you could frame it.
Is A represent a node? Is it
It's like a, yeah, it's the top of the stapler.
Okay, but so it's not a location. It's a, this is what I was getting back to earlier. I kind of view like, you know, a model of an object is it's a space, and then we assign features at different locations in that space. And so I could say, oh, well, the point in space is a node, but that's not what it is. You're saying the point in this case, the A is like a feature that is located at some space location, but that feature can move. So it's sort of like, I've always had trouble, you know, trying to think about the brain as sort of these graphs like this, because there's language that we use for graphs that don't, it's hard to fit on top of this idea of location spaces and features at location. So I'm just confused what A is, right? I mean, I can understand what a node in a graph is.
Right.
But that's why my first question was, well, is it a location? Is it a feature? Or is it a node on a graph?
Yeah. So I would say it's a feature that's currently associated with a location, but that location can change.
Okay, so that to me is
like it's the top of the stapler.
We can call that a
Right.
node, but it's really it's really, but if it's a feature, I wouldn't normally typically think of it as a node. I typically think of a node as a point in some sort of a space, right?
Yeah, it's all the things associated with that point. So it's not just like a feature.
Well, but if it's moving,
then all those things move together.
Yeah, again, the language of nodes and graphs it's just hard.
Like
for me to reconcile.
maybe one way, I don't know if this helps, is thinking about it is like it's almost like a place cell. So it's like bound a bunch of information to it, but the mapping between the place cell and the grid cell, like maybe that could change so that where the place cell actually is changes.
Yeah, okay, but we don't see that, right? We don't see that. I mean, place cells represent a location in a space. So do grid cells, but they're different. But it does represent a location. So you typically don't see a place cell move. I mean, it can represent an individual cell can be firing different locations, but
yeah,
but
it can remap though, can it? And
yeah,
I guess like
it remaps. I'm not sure about that. Does it remap in the same environment? I think I'm not aware of that.
Well, that's the thing. If we're changing the environment, so that's what's
right. If they go to the individual cells.
So the question is like, what's happening when we change the state of an object? Like, is that like changing the environment? Because I think there's things like if you start moving the walls of an environment and things like that.
Right.
I'll
in this case,
touch on this a little bit, but like then definitely the grid cells, and I think the place cells also like distort and things like that.
So I've argued earlier that when the stapler moves, it's the same object, and therefore it is the same space. If we switch to a new space, then all the learning about the stapler would be forgotten. And so, like, if you have an object and I got a model of the object, and then some part of that model changes, well, I have to be able to represent that change, but I don't want to forget everything else. You know,
Yeah,
it's
I
like,
agree. Yeah,
I don't look at it and go, oh, that's not a stapler anymore. It's like, yeah,
right.
it's just changed.
Yeah, no, I definitely agree. Yeah, and I guess I'll talk later about the kind of the space element, and maybe that'll
Okay.
kind of help in terms
Well,
of that.
I
But
do see there's in my mind, and it just could be if I'm stupid, but in my mind, there's a fundamental sort of impedance mismatch between talking about models based on locations and features and models based on nodes and edges, and I don't know how to bridge those two.
yeah, I feel
But
it feels to me like part of the issue is just it was easier to use the language of features at locations because we were always talking about static objects. Whereas it feels like, yeah, maybe it
yeah,
almost needs
maybe.
some new language now that
Maybe it's funny because
things can
I
move.
take the opposite approach. To me is it's like, okay, that language is great. It really works super well.
Yeah,
How do I explain behaviors within that language? And that's how I'm approaching it. I think I'm making good progress on it. So I'm open to other ideas, but it's going to be hard for me to,
yeah.
we're sort of going in different directions here in our thinking at the moment. But maybe I'll shut up for a while, let you keep going, see if I can pick it up.
That's right.
I'm just trying to really understand. Okay, what is A and B exactly? You know,
Yeah, yeah,
I
yeah.
understand
But
nodes of a
hopefully
graph.
that clarified it a little
No,
bit,
not
at least
really.
that. Yeah, I
Not
understand it's
really.
hard to map. Okay, maybe hard to map
That
onto
didn't
the computer science,
really.
but
It
okay.
I
didn't
try
really
to
clarify
like give
it.
a explanation if that's I'm just trying to find like the zoom, whatever I can draw uh to to explain it. But
Yeah.
where's the zoom controls? I'm sorry. Oh,
Oh,
annotate.
you're
I found
you're
I
annotate.
think
asking.
if you hover above the top, at least I
Yeah,
have an
yeah.
annotate. I don't
I
know if
see
you
it.
see one. Yeah, nice.
Yeah. Okay. Oh, thank you, Will. Hi.
You
So
want to draw something? I see.
yeah, yeah. So let's say like instead of a stapler, we have image like a grid. So like let's say a 10 by 10 image. And we can think about this as a graph where like each pixel is a node, right? Can you think of image as like a
So
grid graph?
this is not an object. This is just a pixelated display. Is that what you're saying?
Uh, yeah, I mean, instead of a stapler object, I have an image object and a
Uh,
picture, let's
uh,
say picture.
okay, I'm trying to say, is the object this grid, or is the grid represent where I represent the object? Are
Uh,
we actually recognizing a grid, or is the grid represent a pixelated sort of
yeah,
display?
the ladder.
Yeah, I think for what it's worth, like I think Jeff, as he was saying, like he understands the concept of like the graph and what a node and a graph is and things like that. I think it's more, it is this tricky thing of like how do you map that
Yeah,
onto
I'm trying to get there. I
location?
haven't gotten
Okay,
Okay.
there
I
yet.
just wanted,
Yeah.
I told you, I just wanted to clarify because you said we have,
Okay, so let's say we
yeah,
have like a physical picture, like from
okay.
A4 paper, and I cut them up into little pieces, and so each piece is a node. So does that make sense? For now, like, can we imagine
If you want
that?
to define it that way, sure.
Sure.
No?
Okay. So then
Okay.
each pixel can have each of those little cuts. Let's say we cut it very small enough so that that node, that small piece of paper after we cut up the picture, we can think about it um, as like a set or vector that contains the RGB value, for example, because it's coming from a picture, and also the XY location from where that came from. And that is representing that node.
Yeah, but that's just a purely that's just describing you know an image array. There's no object there, there's no learning there, there's no model there. There we need these things that are moving on the stapler are not just pixels, they're objects. They're like there's features that that there's a model of the stapler, and
Yeah.
it's not just an image. And
Yeah,
so
so like node A, when we learn features at locations, we do learn some kind of color, HSV principle,
yeah, but
temperature.
I'm assuming that Niels presenting A is not just some undescribed pixel block.
No,
It's the
yeah,
top of the
this would be
stapler,
associated with this would be associated with an object in the lower level.
right?
I think the thing that yeah, that you're stuck on Jeff, which I think is a reasonable concern, or like thing we need to understand is like, yeah, we've always described kind of like features at locations, which assumes or kind of frames it as like the location is in some sense like static. And then here it's like there's the reference frame, at least the way I'm thinking about this is like there's this graph that's embedded in the reference frame. But where the kind of elements of the graph
Right, so
are relative to one
it's
another
a
can
stretchy
change.
graph, right? It's a stretchy
Yeah,
reference
exactly. It's a
frame.
stretchy graph.
Right, the
Well,
problem
I guess there's two ways. Either the graph could stretch, or things could be nudged around in it as a function of some time or
right,
yeah.
well, so there's two ways you could do this, right? You could modify the reference frame. And every time I thought about that, it's like, and I know in grid cells, they do get sort of distorted. They're not really, but not a lot. It doesn't explain this. That's this mechanism stuff. But the problem is, as soon as you start modifying the reference frame, it's very, very difficult to do path integration. It's difficult to do metrics between two arbitrary locations. And so
Right.
I just think it's the wrong place to go. You just got to assume the reference frame is a reference frame. That's why it's called a reference frame. It's not a flexible graph. But we can consider this possibility. But I've taken it as sort of baseline that the reference frame is a reference frame, and it can't get distorted because then you lose these desirable properties. And somehow we have to
I think that's why. Yeah, it'll be
Yeah.
interesting discussing, because one of the things that I think it might connect to is like with abstract spaces, kind of by definition, generally they're distorted. Like they're generally not going to just follow kind of Euclidean space, and so like maybe these distortions are on like a continuum.
That's a good hypothesis, but I'm not willing to say that yet. I don't understand. What I'm willing to say is I don't understand abstract spaces well enough to make any conclusions about it yet. And I am saying, look, I do know that it's very, very likely the neural mechanism is going to be the same. So if I'm dealing with physical objects and I have a fixed reference frame, I'm going to start with that assumption for abstract spaces. I just don't know yet. I mean, I just don't have a good sense yet for abstract stuff to make a conclusion. I mean, my intuition might say, oh yeah, things are moving around, right, but I don't trust them. I don't trust that. I don't have any.
Yeah.
I mean, it's just intuition. It's not really any kind of evidence for that. So I don't want to reach that conclusion. But you could,
No, that's fair.
I think, I mean, you said there are two options, and then I think you didn't go into the second one, but I think the second one is actually how a lot of the graph neural networks would model things, where basically we're not distorting the reference frame itself, like locations are still in a Euclidean space relative to a common point, but instead, like depending on the state of the entire graph, you would expect each node to be in a different location in that reference frame.
Right. Well, then a node is a feature of the object, right? And then basically I can say the features of the object can move.
Yeah.
In fact, I was typing it up just before we got here. This, the things that can, I've said this before, but I'll say it again. Every single possible object behavior can be expressed as features moving locations, features changing orientation, features changing ID, and this can happen at one or more locations independently or simultaneously, causally related. And that explains everything. I mean, every kind of transition I can possibly imagine, even ones that are continuous, even ones with whole object changes, but all of them basically say that that you're remapping the model, and those are the things that typically, like in the stapler, the features are moving, and they're moving locations and changing orientation. Where something with a light, for example, the light turns on and off, that's a feature changing. It's a feature changing, but it's not moving. Anyway, so all possible behaviors can be represented by the idea that the graph elements, the features, move, change, and change orientation. That's how
Okay,
I can think about it.
so
I have a quick.
okay, so because that would actually be my preferred way of doing this, but I thought there was some concern around the feature. But Will, you go ahead first.
Yeah, it was just there was one thing that confused me, Jeff. You said that a feature can change its ID. I didn't understand that. What does that mean?
You know, for example, it's let me see if I can a good example. I can make up a fanciful example. I'm trying to get a real world one.
Like if you have
Would it help
Oh,
if you say
here.
the node can change the
Here we go.
the ID
Here we
associated
go.
with it?
So let's take, for example, I'm looking at a screen and there's a letter on the screen. And then I push a button and the letter changes to a different letter. Same location, same orientation. It's now, instead of A, it's B. The feature has changed from an A to a B. It hasn't changed location, orientation, or scale. Or I could push a button and the letter A could move to the right, or I could push a button, the letter A could rotate. I could push a button and a bunch of things happen simultaneously or one at a time independently. So that's an example of a very simple example of a feature changing its ID.
So yeah, I guess I feel like that's why I mean, it doesn't have to be the word node, but I feel like some sort of terminology to capture the idea that there's like kind of a binding element, something that's gathering information, and that can both move and the attributes associated with it, like feature ID, can change.
Well, that's why this one, my very first question to you is A a feature? If A is a feature, then I'm with you.
Okay, but I think that was what is confusing if what you're saying or like asking about, Will, is like if that feature can change, is it the same feature? So I guess that it's like it's the same node, even if the feature changes.
Well, now you switch the node to me location. So
well, but what if both are happening? Like what if you kind of had like almost like a button that displays a letter on it, and that button can move around, but the letter that's on the button can change.
Right.
I don't know.
As I said earlier, let's say you have a model, you've learned the model in our classic way with a reference frame and features. Each feature has an ID, each feature has an orientation and a location, and that defines a model, right? Any one of those components can change, and I can come up with examples for each one or any combination. So it's possible that the feature can move and change orientation. It's possible the feature can move and change orientation and change ID, or any combination of those things. It's basically
I think that's pretty consistent with this graph terminology, at least how it's used in that field.
Yeah.
Is that A, like the node A, can both change the features associated with it, but it can also move in space. Like without distorting the reference frame, it can just have a new location.
Well,
so
then
I think
what makes it, why is it a node? I mean, what makes a node? What's a node in that case?
I guess it's
a collection of information.
To other nodes. It's how it's connected by edges to other nodes.
Well, you can say, well, in this case, the tapes of the staple, you can say, oh yeah, they're all connected to the hinge at B. But I can remember lots of examples where there's no obvious connections at all. You know,
I mean, edge doesn't have to be a physical connection. It can also be a causal connection.
Right. Well, but in this case, it's not clear that. I mean, the A and the B, it looks very physical in this case. But there doesn't even have to be a causal connection. I could just have a feature that changes on its own, just, you know, whenever it wants to. You know, maybe I have an object that randomly changes its color from, you know, at some location from green to red, and you know, it's not moving, it's changing. I think there's so much language associated with nodes. Maybe it's just me, but that we start using that language, you just slide into this thinking about graphs, and I'm trying to say, okay, given I have a reference frame and features, where is the graph you're talking about? You know, A could be a feature.
Yeah, I think it's like a proposed new language. From my view, it seems to fit pretty well what you're describing, but I mean,
I haven't heard that yet. I want to believe that, right? I do. So I can say it's a feature, but you're not willing to say that.
Well, what if we say it's an object? Or
well, an object.
And then so the ID of the object can change, the location of the object can change. Like it's a sub-object.
But that's just a feature.
I mean, you often call a feature, yeah.
And can I try one definition of node? What about defining a node as its feature at location that has edges to other nodes? Like like it seems to me that node is defined because of edges, because edges exist. If you don't have edges, you don't need nodes. You just have features at locations. So what makes it a node is, and there's these features at locations have edges.
Well, all right, you could say that, but I'm trouble with that too, because what does the edge represent? I mean, I could say there's two
Right.
things that change are causally related. I get that. That's good. If I just said the edge is a causal relationship, well, then I can see that maybe A and B are changing, and they're changing in a causal way. But I could still have a node A, which is just a feature at some location, and it has no edges. It's just basically it's at the edges. It's location. That's what it is. It's located relative to everything else based on where it is in the reference frame.
Yeah,
Yeah.
if it has
I mean,
no
and maybe
consistency,
feature
it would
is a sufficient description. I think it's just it maybe is confusing to others in terms of like, or at least to me, in that like sometimes when you say feature, like that just makes you think of like, oh, it's just like the colors that are there.
No, to me,
like
to me, a feature is whatever I have a cortical column, and whatever bit pattern that's coming in that's going to layer 4. I have no idea what it means. It's just someone's telling me this thing exists at whatever location you're at. And that thing could be an entire object. It could be, an edge on V1. It might be just a simple thing on the retina, but it could be an entire feature that was represented hierarchically. In which case,
But I guess
becomes
the reason to move from feature to node is because now we want this thing to actually also be able to change location. So it's not just a feature, it's like a feature and location which can change. So like if I have a pendulum, whatever is on the bottom of the pendulum it's a feature, but that can change location, and
right.
the node
Right. Well,
difference
that's
is basically
right.
that it's connected to the top of the pendulum. And
well,
yeah.
okay, so the language I'm using explains all those things, but it doesn't assume there's a physical connection to anything. There might be, but it doesn't assume it. I mean, the language I've said is that you have a reference frame and features, and those features can change, they can move, they can change orientation, they can disappear, and a new one can appear. That describes every single possible object behavior you can imagine. And there's nothing, it's complete. It's a complete basis of object behaviors. There's nothing else that could happen to an object. So I like that from that point of view. I don't make any assumptions about anything else.
So just to clarify, so you would suggest instead of calling it a node, you would call it a feature, but
I don't mind calling I don't mind any language, but typically the word node means something else. And so it leads to lots of confusion. To me, a feature it's nothing. Don't try to picture what it is. It's just whatever is located at some location, and it could be an entire object. It could be, it could be anything. It's just, in our models, we have locations and things at those locations. We've decided to call the things at those locations features. That's all it is. There's nothing else to it.
Yeah, all right. Maybe is it all right if I move on and then
I just
we
just
can
gonna I just know I think I
reflect
know
on
what's gonna happen. I'm just gonna get lost in this, and it's not gonna be meaningful to me, but I'll try.
Yeah.
Let's keep going on.
Yeah, we can maybe come back if it's an issue. But yeah, so I guess one of the key kind of challenge to representing behaviors is learning the properties of edges. For example, like a kind of rigid relation or something more interesting. So for example, with like a hinge joint, I think that some through kind of serial attention and knowledge of what the close stapler would look like and attending to kind of movement at A, it would be reasonable to argue that you're observing a single learning module is observing movement at A. It had some expectation about where B is, and because of the movement of A, there's now a fixed distance but a change in orientation relative to B. Whereas versus C, it's just kind of moving, like it's just the displacement is continuing to grow. I'm not saying this is like some sufficient or elegant way to learn it, but hopefully this kind of captures just the kind of basic idea that just through the information that we're observing at a node and what we know about other nodes, or what we believe we know about other nodes, you might be able to infer some kind of relations or some of those edges, basically. And I guess just, oh, sorry, go ahead.
Yeah, just bringing back what we, I think, discussed like 2 years ago.
Yeah.
The nice thing about this is that it allows very fast generalization. Like if we learned an edge type before, we can apply it to all kinds of other objects where that type of edge exists, like a rigid relationships or a spring relationship, something like that.
Yeah, yeah. I think there's another way to do that, same learning. But
Okay,
I'll leave that for another day.
Yeah, no, sounds exciting. But yeah, so, if it's necessary, just like another example with like a hinge joint with a spring that's kind of constantly trying to close the stapler. And so, again, A is moving, but this time on its own. And so there's kind of a rigid relation still with B, but also some kind of closing relation, whatever's learning this doesn't need, whether it's a child or whatever, doesn't need to have some concept of spring. They just see that this kind of behavior happens again and again, where the kind of hinge is closing itself. Yeah, okay. Let me clarify this. Yeah, deforms as a function of yeah, features nodes move in the which I'll get back to in a minute. But I just wanted to quickly kind of contrast this with, oh yeah, and then one last kind of thing on like language that people may have come across. So in the sort of like graph neural networks, kind of literature, you'd often talk about message passing, and that's kind of the dependence of one node at a time on the states of its neighbors from a previous time step. And you can iteratively kind of pass these messages and see how the state of the network evolves. And then I think an interesting thing just to think about is a hypernetwork. So a hypernetwork is a network that generates weights for another network. But so you can imagine how, as Vivian was just kind of saying,
weights being what? Weights being like weights in a neural network?
So if you assume that what you call it, the way that this edge is encoded, like the way the influence of this feature on this feature takes place is via some weights. Those might
a neural network weight.
Yeah, like a neural network.
Okay.
Those might not be always the same. Like they might change, and one way to change them in a deep learning setting is to generate a set of weights. But I'll touch on later how this like might connect to kind of more SDR style HTM weights. And then, but just kind of contrasting this kind of graph view with like a kind of global sequence view of behavior, which, if I think we've kind of discounted now, but that isn't to say that sequences aren't going to be useful, and I'll come back to that. But so I think this is how we sometimes would talk about behavior before, where you kind of like have a stored sequence of full object morphologies. So you have like a morphology at time equals t 0, and then 100 others or whatever, and then time equals t. But that's lots of information to store. That the amount explodes with the degrees of freedom of the behavior, and it's, I think, to kind of the points you had raised on Slack recently, Jeff. It's hard because the single LM generally only observes part of an object at a point in time.
Well, I also felt that objects don't have a global state.
Yeah, or at least not one that constrains that is so specific. Like this one is like it's a fully defined state with all.
I argued even this. I argued this one, even this one was not fully defined. It's a poor example, but I talked about the deflection plate at the bottom there. And there's a state of that deflection plate. It can be in one or two positions, or can be in the process of rotating between those positions. And that deflection plate is completely independent. Its behavior is completely independent of the stapler top. There's
Yeah.
also typically a staple have a way of removing the staples, which is sometimes it's a spring at the back, sometimes it's in the top, but that's also somewhat independent. So, and I can come up with lots of examples where objects have lots of independent parts moving. A car,
Right.
the doors are open, the hood's open, the windows are down. I mean, these are all, the car has a gazillion possible object parts of it that are in different states. So there is no global state for a car. Or stapler.
Right.
So that tells you you have to have the state for individual features or components, and it has to be on a location by location basis.
Yeah. Yeah. And so, yeah, I definitely also would agree that a state like this isn't what we want. But yeah, so, okay, so that was kind of brief discussion of behavior, sequence of states. What about space? And so one way we can think about kind of reference frames and how morphology is represented is kind of what I'm going to tentatively call an embedded graph. So features at locations in a reference frame where this is embedded in, some defined space like Cartesian space or grid cells. And this is what we're currently doing with features at locations. But yeah, as kind of discussed earlier, you could have the features change as a function of time or someone pushing or whatever their location in this embedding. Yeah, this has the advantage that you can generalize to novel displacements, so you don't have to do the exact same displacement as you've done before if you just hypothesize that
I don't understand that generally to novel displacements. What is? Are you
so
talking about, I mean, with the position of what do you mean by displacement?
so now I'm just talking about, like, if you forget about behavior for a moment, just thinking about how you path integrate over the object.
Okay, what's the word displacement referring to in this case?
So you can take a movement of like a larger or a smaller amount, for example, than you have
the displacement
previously.
is this displacement the angle of the top? Is that what displacement is representing here?
No, the displacement is the movement of the sensor.
Oh, okay.
That's what I mean.
Okay.
This is now nothing to do with behavior. This is now a sensor moving over the object.
Okay, all right. Well, you're showing the stapler. So, okay. So the general advantage of grid cells is they path integrate, and you can do that in novel directions, novel displacements.
Yeah.
Okay.
Yeah, sorry, I did think about changing the object to something that didn't have like a clear behavior, since we're just talking about path integration here. But then, anyways. But then
I just
wanted to
it's just
back.
I don't often use the word displacement for that. I'll just say,
Okay.
movements.
Movements.
Right, path integration of movements.
Yeah, okay.
Question.
But yeah, sure.
And we're still talking about space reference frame per object, right? So it's not luminiferous ether out there that everything is in. It's Cartesian space per object. It's grid cell space per reference frame per object. Yes.
So yeah, so I guess for us, we're currently representing. I guess it's a unique Cartesian space per object. In the brain, the grid cells would encode multiple objects in their kind of distributed code.
Be careful.
Probably would work.
Be careful because we've done the same thing in two different ways here. The way we've done it, if I understand it, in our code today, is we've just picked different places in a very infinite space, and we said, oh, over here is where we're going to represent staplers, and then over here is going to represent something else. And so they're in some sense in the same universal space, but they're so far apart that there's no interaction between them, right? So if I know my location, I know what object I'm on. Grid cells achieve the same result, but in a very different way. And if you don't know it, I'm not going to be able to describe it right now. But you have the same set of cells, but their combinations are that once you've locked onto an object, the patterns you'll see in those cells are unique for that object, and you won't see the same pattern on any other object. So it achieves the same result in a different way. But they're both achieving, essentially saying you have in some sense, a universal way of representing space. It's a finite set of resources to represent space, but when you actually represent an object, you've locked into a particular part of that large space that only exists for that particular object. In both grid cells
Yeah,
and
and
art.
I guess
So-
was your question like hinting at a concern, Kristen, or
No, just checking
you're
and
just wondering?
understanding.
Okay, yeah.
It's very different than when we typically think of Cartesian. This is really a really important point, Tristan. So I want to make sure everyone gets it. It's not like, oh, here's, we have some three-dimensional space and we're going to represent an object in one moment and another object in that space, another moment. It's like the objects are so far apart that you'll never get between them. It's like technically you could, but it's infinite almost. You can't. So they're like completely different spaces. I hope that makes sense.
Yeah, and I guess just in case, like to match it exactly with the code, it's not like in the code we move them at like far away distances in the same space. The objects are actually all represented around like a 0, 0, 0 location.
I thought you told me I missed up. I thought you told me that. I thought you said no. The points are totally unique.
We
so
could do it that way. It's like mathematically
like,
equivalent.
each of them
I-
are basically their own space. So it's like basically like that reference frame has a unique prefix, and you would only index that reference frame if you're looking at this object. So we could ever move like a large distance and accidentally get into a different object's area.
I see. That's not as powerful as I thought it was. You're basically using the object ID as an index to say, okay, now this reference space is representing object A. Is that what you're doing?
If I understand you right, yes, but it would be pretty much equivalent to putting them at very far distances. Like we could put them at very far distances. It's basically we have these different hypotheses of where we could be, and either we put the hypothesis of being like at very far away distances in the same space, or say we could be at this location in this reference frame, or at that location in this reference frame.
So if I want to predict what feature I should expect to see, I just can't look at the location. Is that right?
Yeah, you could. I mean, it's
How?
basically if you would imagine like each of the locations having a unique prefix depending on what object it is.
Right. So you're basically using an object ID to say how do I interpret this space? Okay, I get it. That's not what I thought you were doing.
But
it's kind of almost like a fourth dimension that we move along, or I don't know.
Right.
It does feel like it would be equivalent, except for the slight risk of interference that we don't.
No,
that we avoid.
I'm not sure it is. Maybe it is, maybe it isn't. But one of the things that neurons do is in some sense, you need to know that prefix to do anything, right? And that prefix is I assume, a hard-coded prefix, right? It means that you have a prefix that represents cups and prefix that represents staplers. Is that correct?
But you don't need to know it. You can test different ones at the same time.
Yeah.
I thought it would be equivalent because if we place them very far apart, we could do it exactly with a prefix, like adding whatever large number in front of it.
Right. Maybe. This, and I don't understand the neurons well enough in this case, but when we're trying to do inference, it might make a difference under certain circumstances. I didn't catch it. I see what you're saying, Vivian, how you think a prefix is sort of just like more bits in space. It's not clear to me whether that's equivalent or not. I'm not going to accept that yet. Okay, I'll let that go.
So just the last thing to say with these kind of embedded graphs is like this works really well with kind of 3D Euclidean space, but it's a bit more confusing how we kind of would embed kind of abstract or arbitrary spaces into this, like a family tree or whatever. If this is sort of substrate that we're using, like how do you understand that certain parts of space connect you to other parts in space, but others don't? And yeah, I won't go into this too much, but yeah, just that there's some evidence that these grid cells can distort, but I think it's a fair point, Jeff, that this is generally not very significant. So I do think a better way of doing what we were talking about before is just having that like features basically can move in this kind of space.
Mhm.
But then the other kind of way of conceptualizing space is kind of graphs as sequences. And this is actually quite related to what we tried for a bit in Monty, in like before many people joined, but in fact before I joined, which was features at displacements, where you kind of learn space as a sequence and build a graph from that. And this has the kind of advantage that you can, like in normal kind of 3D space in the real world, you know, generally those kind of displacements or kind of movements are very simple and kind of follow, you know, the same behavior you'd expect here. But you can imagine in some more complex or more abstract spaces, sometimes you can move between points and sometimes you can't. And so that will kind of, those displacements will kind of carve out this potentially, abstract graph-like structure. And it's important to note here, these kind of green arrows, these aren't the same kind of edges that were in the earlier plot. Like the earlier edges were about how one feature at a point in time influences other features, neighboring features at a point in time. So that's like a causal relation. This is a connection in movement. Like this is the fact that you can move between one of these to the other by following this displacement. But what we found with when we tried to do this with the features of displacements learning modules was that this tends to struggle with novel displacements in the sense that you end up kind of trying to match these movements exactly, which is fine if you're operating in a discrete grid world where you're always going like up one, right one, whatever. But you can imagine if you move only 1 centimeter or 1.5 centimeters instead of the 3 or 2 centimeters you did when learning, it can be hard to match these. I've been trying to think about like some sort of like hybrid stuff that might address a bit of this, but yeah, I didn't make as much progress as I wanted, so I'll talk about that another time. But I guess
Yeah, I mean, this could be, I mean, this could be very confusing for people who have been here in the past. Basically, we were trying to represent models, and there's two basic ways you can do it. You can say these features are at some location in some reference frame, or you could say these features are at some displacement from each other. Of course, if you're trying to figure out, you know, physical displacement, like Niels was saying, some direction, distance, and there's a real power in doing physical displacements, but there's a combinatorial problem of, you know, obviously if you have a lot of features, trying to represent the displacements between all of them is impossible to learn. It takes too much memory. And so there was we were struggling, like, what is the basic representation of an object? And these are the two options we were looking at.
Yeah, and this was actually the very first learning module that was implemented in Monty. And it had some really nice properties, like doing it this way, we can actually represent displacements in a rotation invariant way. So we could recognize objects in any rotation without specifically testing rotation hypotheses and like going through the different options. There were some nice properties of it, but yeah, like Niels and Jeff said, the issue was it's not really path integratable. We couldn't take new movements that weren't stored in the graph.
Yeah.
Yeah, and that, I guess for what it's worth, like if you are operating in a discrete kind of grid world where, you know, something like this, where you can only move up by one, left by one, so forth, that those kind of issues go away. And so this kind of approach has been used a lot, for example, in Dilip George's work, this I was meant to say clone structured cognitive graphs and the Tolman-Eckenbaum machine, which are kind of ways of showing that, you know, if you visit all of these edges, even if it's a kind of complex graph, you can build this representation. And And then you can path integrate on this, and you can follow, not like, even though you visited every edge, you can follow an entirely novel path. But like, for example, in this one, the way it's being learned is actually with this kind of sequence memory that's definitely kind of has similarities to hierarchical temporal memory, in that, although this doesn't look like a sequence, if you basically follow a sequence, you can build up all of these edges, and that forms like a graphical structure. So then kind of going back to behavior, and trying to kind of bring this together. So now if we're looking at this model again, where, okay, now the edges are representing kind of more causal relations between these features. So the kind of local states associated with a feature or node are going to follow a sequence over time. And that's going to depend on, as things we talked about earlier, like the local actions, incoming states and edges. And then I do think it still makes sense that there's some global state that's like pooled from all of the local states. So it has some information, but it's not like a one-to-one mapping between, like, yeah, this base plate or whatever.
What's your argument for that? Why do you think there's a global
Because
state?
I guess the main thing is to pass that information up the hierarchy. Because, like, in the same way that this state is the state of the learning module lower down in the hierarchy. So, like, to summarize, that the stapler is closed is useful information when I'm looking at my office desk.
Right. Although as I said before, this is problematic because there isn't a global state. And so I can imagine an object that has multiple different types of states. And in one context, one of those states is important to pass up. In another context, a different state is important to pass up. I don't have a solution to that, but there isn't a global state. I've come to
I guess I feel like it's kind of like object ID. Like, so I put together a slide for this point, which, just in terms of like, you can have changes, subtle changes in morphology, and but the kind of object is still going to be the same object. It's still a mug, and so forth. And like, knowing it's a mug does not tell you exactly where every feature is on in space, in the same way that knowing the global pooled state doesn't tell you the state of every local element.
Yeah, I think the answer to this question is the whole trick for compositional structure was that even though we can pass up an idea of the feature, like there's a logo at this location on the cup, but it's actually, the pairing is done by a location basis. So on the back path, the downward path, we associate the location of the parent object with a specific location on the child object. And therefore we'd be associating, in this case, we'd have to be associating a specific state, a state of a particular location on the child object. So it's not clear to me. I have to pass up the state of the object to the parent. Maybe I do, but by pairing the location on the parent with the location on the child, I now basically can specify the local state of the child object.
Yeah,
if you follow that.
I mean, I think that's useful. Like, again, in the same way that it's useful with the object ID and morphology, like, it's useful to know the overall object ID, and it's useful to know where you are on
Not
the
just
object.
useful; it's essential if I'm going to make a prediction about something. If I'm going to make a prediction, I have to do that.
Yeah,
That was a whole compositional object struggle.
but yeah, I guess to me it feels like, yeah, that providing that information like L2, L3 or something, so that, like, it's just would
yes,
be important for.
I think the answer is going to be different.
Yeah.
I think the answer is going to be, because this is what the surprise of the compositional structure is that I don't pass up the state to the parent, but the parent associates its location with the state of the child. I can't say for certain yet, but that would be
Yeah.
my guess that that's what's going to happen.
Yeah, I guess it'll
Because
be
there's
clear
a-
when we get back to the motor
just
policies,
remember
like-
the state, again, if you accept the fact that there are different states for the stapler, they're not all tied together, and many objects have lots of states, the car. And the parent object can't know what those states mean. That's the whole point of it. The parent object can't, if I'm a car, if I'm representing a car, I can't represent the window at the same time, and whether the window's up or down, or whether the door's open and closed.
But you might represent like the car's on or the car's running.
There are things that I would know about the car, but I can't accept all the individual states of the features of the car. I have no way of interpreting them. I don't want to store them. That the whole point is I can't store everything everywhere. So
Yeah.
I think
No, I
the answer
agree
is
with
going to
that,
be,
yeah.
you know, I would start where you were, Niels. I would originally think, oh, we have to pass up the state. I'm not so certain of that now, and
Yeah.
I think I'm actually working on the assumption I don't have to pass up the state.
So if we
just like-
have a more global state, how would like more, I guess, broader state information spread? So for example, if I touch an object and I recognize its temperature, like I have a coffee cup and I notice it's warm just from touching a small part of it, I immediately know that the whole circumference of the cup will be warm.
Well, let's take a more. I think that's a little bit more. It's an example of one that's. I can come up with a simple example that has the same problem. How do I associate of some observed feature or change in feature? Let's say with a change in a feature in another modality or on another part of the object. It just gets back to the lamp, right? I press a button on the lamp. How do I associate that with the light turning on? They're in different locations. In fact, I might press a button and the light turns on in the next room, right? So I have to be able to associate these changes, and I can do it across modalities. I think that's a broad. I'm trying to. I think it's the same question. It's actually the answer is the same to what you were suggesting, Vivian, which is like I touch it warm. How do I know it's warm everywhere? Type of thing. We have to learn these things. Anyway, that's what I'm working on right now, and I think you can put some parameters on it. So I think you know, imagine you have a whole bunch of columns, and some of them are observing changes at this moment in time. Things are changing of what they're observing, and some are not. So let's say we have a voting mechanism. It's not voting is not the right word. We have a long distance connections, and if two columns, no matter where they are, if their state is changing at the same time or in close proximity in time, we might want to just associate the two to say, hey, when these two changes occur at the same time, and they could be in the same modality and different modalities. One could precede the other, it could follow, there could be a slight delay between them. If there's a bigger delay, then you wouldn't catch it. You wouldn't catch the causality there. So I think there's a general question is, if a column observes a change, how is it associated with other changes in other columns, whether they're nearby or far away? And that's a pretty simple mechanism to do. I'm working on that hypothesis right now. And then you can learn sequences of those as well, using the sequence memory we have. So I could say A follows B follows C and so on in different locations or in different modalities. It's a very different language than you're talking about here with graphs and so on. At least I think about it.
Yeah. Yeah, I guess unless you wanted to ask more about that, Vivian, I've just got a few more slides I can just finish.
Yeah, go ahead.
I just
I
thought
don't know if we were
close
talking about
my
the same thing or not. Yeah.
Yeah, so anyways, global states may or may not exist, but anyways, if they do exist, you know, they could follow some sort of sequence over time. And then yeah, the morphology, I said, or kind of how a movement is going to map onto what you're going to observe is going to be influenced, is going to change as a function of the local state. So as this moves, if you're on B and you move up here, you're going to predict something different versus if this hasn't moved. And maybe that's changes kind of in or to the graph space, or maybe that's kind of related to changes in the sequence describing the space, like this kind of this more kind of view of space. So it just kind of felt like thinking through this that a lot of things in bold here can potentially kind of, just come down to sequences. And I guess this was interesting for me because often when I was thinking about this kind of more graphical representation of object behavior, I was still thinking a lot of it about in the kind of sense of like, nodes interacting and that sort of thing, like in a graph neural network. I wasn't really thinking about it as sequences, but it feels like it could kind of generally all be framed as sequences. But it's just important that there's local sequences, and these sequences are dependent on one another.
If by sequence we mean time-based, one follows the other, follows the other. Is that what you mean by sequence?
Yeah, but also conditional on other things. So,
Right,
so
but
the sequence tradition, yeah, can be conditioned on an
'cause
action,
I-
it can be in the state of neighbors.
right. There's lots of ways. Yes, but so the way I've been working on this and thinking about it is that sequences sometimes occur, and temporal sequences occur, and we have to be able to learn them. But often state changes are not temporal sequences. Things can happen simultaneously and change all at once, and that's it. There's no sequence. There's no time involved. The features of an object can change, and then it stops. But sometimes those
Yeah,
things.
so I guess it's not always like time, but something has to change. Like
Right, but it could, but there's basically causality in space and causality in time, and both of those can occur in any combination. So, several things can change all at once, and I say, oh, they're correlated because they consistently change all at once. Or I could say these things change in sequence, and therefore they're a sequence. But I don't think everything's a sequence. That's why I said it's you meant by sequence time, and I think not all. Lots of examples. I can come up with examples where time is not involved.
But I mean sequences in a state changing from to another state.
Well, that's why I asked you if there was time involved.
Okay, sorry.
So changing to another
then I
state.
answered that incorrectly.
Right,
Not
right.
necessarily.
So one says that actually time has expired, and just one says things change simultaneously. I mean, you call it, to me, the word sequence implies more than one element changing, right? You've got a series of things. But there are behaviors where there is no time involved. If you're just saying, then I wouldn't use the word sequence. That's well, at least it's confusing to me to use the word sequence for that.
Interesting. Okay.
I mean, that's why I said, is time involved? Is there a sequence of elements? Is it some time expire?
Not necessarily. I mean, yeah.
Okay, but that's why I asked, because I said, well, that's how I interpret sequence.
Time is always involved in the sense that like nothing can change without some infinitesimal small amount of time.
Right.
So
but
yes, time is involved in that sense, but it's not like a sequence of like, oh, every 1 second something happens.
All right. Well, often things are like that. The stapler opening is a sequence.
They can be, but I'm saying that that's not what I'm saying.
Again,
all sequences are.
I've learned over the years that I have to challenge every word, because I know often we use the same word for different things. And that was the very first you used the word sequence. I said, what did you mean by sequence? Is it a mean?
Yeah.
I meant, does it mean a time sequence? And because there are lots of examples, we can't rely on that. There are many examples where there is not a time sequence. Yes, obviously time has expired, but it's not like a series of elements over time, like the stapler top. Many things are like that, but there are examples where things aren't like that.
So I guess just one thought, irrespective of whether time is involved or not. One thing that I always worry about a bit with representing your sequences, but I think I already mentioned when I presented some slides before, it might not be a problem actually, is that sequences are a bit similar to displacements. So if you have just a just 1 degree of freedom where you have the stapler opening and closing, it's easy to imagine it as a sequence. But if you have more than 1 degree of freedom, like a joystick that can move
Right.
in all directions, it's a bit harder to imagine how that's modeled with discrete sequences. But
It
then
wouldn't be.
one thought I had was like a lot of these things, we might actually be able to learn all the different sequences, and we could have like small subsequences like moving left to right, right to left, up to down, down to
Exactly.
Right.
the general set to all the joint type objects. So I think
Exactly, yeah.
in practicality, I think that's what I mentioned before, is I couldn't think of an example where we would encounter a completely new behavior where we couldn't have learned all the possible subsequences. So maybe that's not an issue, but just to throw it in there that with sequences, it seems like we would have to at least once observe all the possible sequences to be able to path integrate.
Yeah, and
between them.
it basically, it's kind of similar to observing all the edges in this sense, but like if you just do that in a local one and there's some way you can generalize that to broader spaces, then it's less of an issue. Because yeah, I agree. Otherwise, it's way too many states to learn.
You know, one of the
Um,
nice things about the HTM sequence memory is that it always tried to learn sort of indefinitely long sequences, but if it doesn't get exposed to, it'll learn shorter segments. So, you might start off by saying, hey, I'm learning how this joystick moves through some space, but it doesn't repeat. And the only parts that repeats are sort of local actions. And so it just picks that up automatically. You don't have to, that was one, I just pointing out that it's sort of a natural property of the network. It figures how much it can learn and it'll expand beyond that. If there's some long sequence that you repeat over and over again, it'll learn it, but mostly it would just learn the short subsets that it sees often enough. So it just handles that problem nicely.
yeah. Yeah, and I guess on the HTM stuff, I mean, it's definitely not the developed thought, but just
By the way,
yeah,
when
what I
you
want
use
to
the
think
word
more about is
can I ask a favor? When you say HTM, it doesn't mean anything to me at this point in time. So we
Okay.
have the sequence memory, we have the neuron model.
Yeah.
On its own, it doesn't mean anything. So if you want to say the HTM sequence memory, I know what that means. If you want to say the HTM neuron model, I know
Yeah.
what that means. But HTM is a thing. It doesn't mean
Right,
anything to
and
me.
it kind of overloaded. Yeah, I mean the
Right, so I
sequence
don't-
memory,
Okay, so we need to
but
just say
but
sequence memory.
in the way that could be like conditioned on object ID, it just seems like that kind of conditioning, which was implemented via the dendritic prediction and stuff, could naturally be useful for things like conditioning on states of neighbors, conditioning on actions, conditioning on global state.
It basically,
and
I look at
yeah.
it a different way than you look at it. I just look at it as if I have a neural representation of something and it changes in a consistent, in a repeatable way, it'll learn that. So anything that transitions over time and repeats, it'll learn it. So, and you can put like global state or actions. I don't know. Are these things changing over time? If they're changing over time, it'll learn it. If it's repeatable. So I'm just
I guess
letting
the
you know.
way what this
you
would,
and I, you know, I have very different mental pictures in our head when you use these words. I can tell that.
yeah.
And I'm just, it's hard for me because I have this picture in my head and you're putting these words out there. I'm like, oh, do those words represent what I'm thinking? I don't know.
Yeah, I guess what I'm trying to kind of, in the original temporal sequence memory, you had the kind of L3 layer with the object ID, and then you were going through different features, and depending on which object it was predicting by the apical dendrites, as far as I remember, different SDRs for those features. And that was the kind of unique fingerprint for the different
it's the same, the
different
HTM
objects.
sequence memory is exactly the same as using the reference frames and the features of reference frames. You have a series of SDRs that all represent the same object. and then you do temporal pooling, saying, okay, these all have to map to some constant ID.
Yeah.
So whether it's, whether the sequence is determined by movement of the sensor and what you sense, or whether it's determined by time, it really doesn't make any difference. It's a sequence of SDRs that get pooled to the same ID. So it's really it just says there's two ways you can represent a unique, you can find out a unique representation of a point in space, and that's one through time and one through movement of the sensor and keeping track of the location.
Yeah, maybe it would be helpful at some point. I can put together a slide actually kind of showing diagrammatically what I mean.
Yeah. Well, I just want to make sure it's also important for new people here. It's like
Right.
the sequence memory and our memory reference frame are really just two flavors of the same thing. They're really not fundamentally different. In fact, Subutai wrote a paper on that, I think. How you can mix and match them. They just naturally combine together. So for example, imagine I move my finger over an object in the exact same order every day. Well, it'll learn that. It'll learn that as a sequence, like a melody. But the first time I didn't have to do that. I could move my finger in random order. It just all achieves the same result. That may not help. Okay.
That was everything I had though. Yeah, I'm just trying to find the paper, but we can do that another time.
Well, I wanna try to reconcile what you're presenting with how I'm thinking about this. And I think I need to do a similar presentation to what you did, and I needed to say, here's how I'm thinking about these same issues, and see if we can come to some agreement on them. So I'm working on that. I wasn't working on the presentation, but I'm working on the ideas. So maybe I can present that next week. Is that okay?
Yeah, sounds good.
I think my presentation won't be nearly as nice as yours. It's probably just words, but maybe I'll throw a few images in there. I think during today's conversation, I threw a lot of the ideas out there because I'm trying to match them up to what you're presenting. I want to come to reach consensus on this. Okay.
Yeah.
Yeah. I'm just thinking.
Yeah, I hope. Yeah, I hope I didn't assume too much in terms of like HTM and stuff. If it's helpful, I just thought we could kind of look briefly at.
Well, this
this.
helpful for who? I made this figure, so it's not going to be helpful for me, but maybe other people.
Yeah, I'm also reminding myself, but yeah, maybe this is better for another meeting. I'll just I'll try and do a recap of HTM sequence memory and then how it might be related to sequences behavior states.
Again, I'll say it again, just maybe repetition might help. I don't know. You got a layer of neurons. They're representing something in a sparse way, and the HTM sequence memory was basically explaining how you might come up with a sparse representation and what would happen if you went through a series of these SDRs in the same set of neurons, and they could learn arbitrarily long high order sequences in a very powerful way and make predictions about what's going to happen next. And it does it in a very simple way that matches biology beautifully and explains a whole bunch of stuff that no one explained before. So that's all it does. And so I'm constantly thinking like, oh, if I have a variable, state variable, that's changing, that state variable is going to be on a location basis, or can change on a location by location basis. And that state variable now is also changing for whatever reason. Then I can learn sequences if it changes in a consistent way. And if it's not consistent, then I wouldn't learn sequences. So that's how I'm thinking about learning behaviors and learning causal relationships, behaviors, and all this stuff in the back of my mind. Oh gosh, this stuff is hard.